Okay. So I'm going to talk about applications of AI today. I know you folks have looked at your course structure. I think you've taken some basic methods in machine learning so far, right? So what methods have you covered so far? Quick list, please. Do you recall any? Okay, so you have done linear regression, robotic regression, SVM, etc. And I think you have done the structure of an artificial neuron and how neural networks work. Yes, at a basic level. So this lecture will be about looking at where all of this is going. Okay. And not just from a perspective of generative AI, which is the in thing at the moment. Right? I assume everybody here has used ChatGPT. Yes. Hands up if anybody has not yet used any of the chat application. You have. Good. Hands up if anybody has not used these applications to solve your homework problem. Good. Nobody is a liar. So we'll look at what else can we do, okay, in terms of working with practical, real world, physical things. So it's not just going to be about software-based AI applications, but it's going to be about how do you plan the physical system operation using AI? How do you actually go down to the hardware level and see how AI applies to robotics and why? Okay. So there will be a few recurring themes appearing again and again through this lecture. First thing is, of course, what we talked about just now, which is you should not be equating AI, the broader term, with just generative AI. There are many forms of it, some of which you have already started to learn. Okay, supervised learning, logistic regression, linear regression, etc. All of these are part of AI, at least from the machine learning perspective. The other thing you will notice is when you start to build AI applications or real world systems, you'll find that AI is not one single thing. Okay, so you can't just take something like ChatGPT and build an application completely around it. For you to do anything practically useful, you will have to combine multiple types of AI, maybe supervised learning with unsupervised learning and an LLM on top. And there might also be parts of your system which are not AI. Effective applications will have some pieces coming from AI and some pieces which are not AI based as well. And if you ever have a question in your mind about what exactly is happening in an application that you're building, why it is not working or why it is giving you surprising results, we will see that it's always useful to return to the concept of how a single neuron works, how an activation function modifies the inputs, how different inputs get collated into a single neuron, and what causes it to fire or not fire. And if you go back to those fundamentals, you will should be able to figure out what your application is. And the last is, of course, a warning which we have heard before, which is avoid anthropomorphizing whatever your AI application is doing. Are people aware of what this word means? Anybody? What do you mean by anthropomorphizing AI? Do you know what anthropology is? Somebody murmured something. Yes. So anthropology is the study of people. What does morph mean? Shape and form. Right? So what we need to avoid is to give AI the shape and form of human beings. Okay, these remember are simply at the end of the day function approximation and probabilistic mathematical model. They do not have wishes, need, wants, long-term plans or anything of that sort. They are simply mathematical models. So whenever you're trying to debug an AI system, you should not think of it as a human. You have to think about it in terms of mathematical functions and approximations. Okay, so that's going to be the recurring theme of what we see today. So to give you some context on why AI for robotics, we need to look at a little bit of history. Okay, and specifically the concept of Industry 4.0. Have people heard of this term before? You probably have seen it in newspapers or popular magazines. The idea there is that we are currently talking about Industry 4.0. So this is a popular term to describe the phases of industrial technology that people are using right now for manufacturing, robotics, etc. Okay, so these are what are called cyber physical systems. Cyber in the sense of connected to the internet, and physical in the sense of actually manipulating real world objects rather than staying in the cyber. Okay, and the reason people say we are in the fourth level of industry is because they typically divide up industrial technology into these four parts. Now, remember, this is not like some discrete date on which you move from industry 1.0 to 2.0, etc. These are logical divisions. But the rough idea is that very early on, industry 1.0 was simply about mechanizing things that people are doing by hand or using horses. Okay, so think of this as the first steam engines kind of thing. In the second set, electricity became ubiquitous, easily available, and so people started powering your industries not by steam or coal or oil, but by electricity. In the third phase, we had automation, but not intelligent automation. Okay? So these are repetitive tasks such as assembly line stuff, movements of robots being done at a programmatic level. So somebody hard codes what motions the robot goes through to be able to manufacture a particular product or part. But it doesn't have any intelligence. It doesn't adapt to what new requirements coming from the users. Okay, and so when we say Industry 4.0, the idea is that we are merging the physical manipulation capabilities of robots with the flexibility of AI algorithms to be able to adaptively manufacture new things. So, as an example, you can think of a car assembly plant. Okay, right now, when you go to buy a car, maybe after you graduate and you have enter your first job, you will be looking to buy a car. You typically have a few discrete options in a particular car model. Okay? So you get a choice of maybe 4 or 5 colors and a few different colors of the interior, etc. Okay, not much beyond that. And the reason you are so restricted is because these robots have only a fixed number of settings in them, a fixed number of programs available for manufacturing particular models of cars. In the future, maybe even within 5 years' time, there will be the assembly line that will give you choice of any material for your interior, any color that you desire, any different types of engine requirements, etc. And these will all be manufactured on the same manufacturing line. Okay, so all the robot will get is a target for what needs to be in the car. And the team of robots, multiple robots, have to figure out how to coordinate which robot does what job and where it brings the colors from, etc. All together to be able to manufacture a car that is customized to your specific requirements. Okay, so that's the reason why people are starting to use AI. And the reason is that when you have multiple robots talking to each other, say any different robots on a manufacturing line trying to talk to each other, how many possible communication channels are there between an order of n number of agents? N squared communication channels, right? So if you have 3 robots, they can talk in 6 different ways, NC2 basically. If you have 100 robots, they can talk in a very large number of different communication channels. And that's the number of coordination activity you have to undertake. Okay? So it's not that it's impossible to write a program to manufacture a car that is customized to your specific case. But the time it would take to write such a program to coordinate n square different robots is so large that it doesn't make economic sense for a manufacturer to give you that option. Okay. But if you have AI-driven, machine learning-driven robots which can figure out what to do on their own, then the number of programs you have to write is 1, okay, which is the logic for what goes into each robot. And then the data that the robot receives drives what it actually does. Okay, so you write one machine learning algorithm or one AI-based application put it on each of these robots. The same software application goes onto each robot, and they will figure out what to do on their own. So you have solved the n squared communication channel problem by writing one particular application. Okay, so that's why we are looking so deeply at AI applications right now for this new era of personalization to individual tastes. Any question on this so far before we go into specifics? This was like the high level introduction for what we're doing. Okay. So let's look at two examples. Okay, one that stays in the virtual world and one that actually affects the physical world. And these are going to be motivation for looking at AI applications for you, since you're taking an introductory AI course, and for you to think about where all of these applications could go. Okay, so you know right now that in early April something big is happening in the financial world. Have you read this? What is happening? Why are they crashing? Who's damaged? Okay, so what does that cause? Okay. So, in simple terms, what has happened is that the US has applied import taxes or tariffs on a large range of products. And that means that if you are shipping something to the US, either you or the person who is importing it has to pay an additional tax to get this product delivered into the US. And this means that you have to spend more money, and that money typically goes to the American government, which can use it for different purposes. Okay, but as a private investor, if you are investing in a company that imports stuff into the US, then you have a lower projection of profit, and that's why you have much lower share prices, etc., for the moment. Okay. So what typically happens is these kind of financial shocks come in all the time, and the type of investment that they typically affect is more equities. Okay, so these things are equities. So the range of returns you could get from an equity type of investment in direct shares in a company is pretty large. So on average, you can get 12.5% in the short term, but it could go as high as 50% or as low as minus 41%. Okay, so it's a big spread. In the between, you have something called debt kind of markets. Okay, so these are investments in more secure things, which give you a lower average return, something like 6.1%, and have therefore lower volatility around this mean. And there's a third type, which we don't need to go into right now, which has an average of 9.1% with plus minus bands up. And this is in the short term. Okay. As you go farther out, the later bar charts tell you what are their projections for the long term. Okay. So you will have heard that even in India, in 1 year you could get plus or minus return, but in the long term, equity is generally return around 12%. So you see that as you go farther and farther out in the future, the averages stay roughly the same, but the volatility around those averages is lower. Okay. Now think of an AI application where you have a certain amount of money, say 1 lakh rupees, and you are targeting a certain final amount, say 2.5 lakh rupees, 10 years from now. Okay. So you have to pass through different levels of volatility in the short term, long term, medium term, etc. And make sure that you get to 2.5 lakh rupees at the end of the tenure, which is 10 years. So what would you recommend? Should you pick any one of these? Should you keep moving your investments? What do you think intuitively you should do to get from 1 lakh to 2.5 lakh in 10 years? Ideas? How many of you currently have stipends for last year, etc.? Nobody. So you're not earning money, so you're not going to worry about what happens to your money in the future. Good.
11%. The issue is like right?
Correct.
I mean, a good equity research for a long-term basis, to make 1 lakh into 1.5 lakh in 10.
Good. So at an 11% return, which you can see at the end here, and with a low enough volatility, because we are looking at 10 years, you can go just for equity, and you can be pretty sure that you'll get to 2.5 lakh rupees in 10 years. Okay, that's one customer's requirement. Now somebody else comes in and says, I have 50,000, I want to get to 70,000 in the next year, and so on and so forth, right? So if you are somebody like an investment firm who is servicing a million different customers, each of whom has a million different requirements on what they initially want to start with, the amount of time they want to invest, and the final amount that they want to get to. Then to navigate through all of this volatility, you cannot have a program that you write to solve for where the money goes, especially because every year or every quarter you have to rebalance where their money is. Okay. Also remember, you don't have to put 100% of your money in one of these. You can split it, right? And you can split it in an infinite number of ways. So the idea is that you need a flexible algorithm to manage your money if you're serving a very large number of customers, because you cannot afford to solve specific optimization problems, robust optimization or stochastic optimization problems to figure out where their money should go. In an algorithm which is trained on financial markets and is trained on managing money. So this is one application where you can think about applying AI. Another one which directly affects the physical world and which I'm sure you have interacted with before is the Amazon problem. Okay. The Amazon problem is as follows. Look at Amazon's delivering to Mumbai on a particular day, like today. Okay. Do you know where Amazon warehouse is in the Mumbai area? No. Have you bought anything from Amazon before? Nobody has bought anything from Amazon? You have it. So have you seen your order status details ever?
And save ship
Correct. Okay. So the Amazon warehouse for the Mumbai region is in Bhiwandi, which is north of Thane, heading towards Nasik. Okay, it's maybe 1.5 or so hours from here. Now you will have 100 different trucks that Amazon owns sitting at this warehouse at 4 a.m. on any given day. And you have thousands of orders which are coming from Mumbai for very different parcels, which have to be delivered on that particular day. Okay. So the Amazon problem is, how do you manage these 100 trucks? What parcels go on to which truck? And where do you send each of these trucks? So that the delivery cost is minimized while still satisfying the time limits you have agreed with Amazon for delivering your parcel. Okay. So the optimization problem that you're seeing here, I hope everybody has seen some sort of optimization problem before, right? Even for linear regression, you saw the least squares problem. Yes. So you are aware of what an objective function is. Agreed or not agreed? Okay. So the objective function that Amazon solves on every day is as follows. You have the objective J, which is to minimize, given these three different actions, we'll come to what they are, minimize the amount of distance traveled by the entire fleet on a given day. Okay. So the distance traveled is an approximation of the fuel consumed. Okay. Maybe it doesn't really work for Mumbai, but for the sake of argument right now, assume that distance is proportional to fuel consumed. So the distance traveled is given by these factors. The first is, where does vehicle I go at the initial time? Okay. So if vehicle I goes to customer K on as its first trip, then the distance traveled by this vehicle from I to K is from the origin point to the location that it's going to first, that is V0I. And similarly, the last term is about the last leg traveled by this vehicle. Okay, this is the last leg traveled by the vehicle back to the warehouse. And then in between, you have this vehicle K going from customer I to customer J. Okay. F, L, and A are binary variables. So if the vehicle K goes directly to J from I, then A ijk is 1, otherwise it is 0. Okay. And so if you have a graph that consists of all the possible customer locations like this, okay, and if this is customer 1 and customer 2, then if there is a connection here, if there is a vehicle traveling like this, then A1, 2 for that particular vehicle will be 1. And if it's not gone this way, then this particular variable will be 0. Okay. So you can convince yourself that if you just count all the numbers that are 1 among all of these particular variables, and then you sum up multiplication of that 1 by all these the distances, then the total distance covered here is the total distance traveled by the whole fleet. Okay, so you basically have binary variables indicating which edges in the graph are actually activated. And then you have the summation of all of those activated edges. Those distances give you the total distance traveled by the fleet. And this is what you have to minimize. Okay. So what are the decision variables here? In optimization, you will remember there's an objective function and there are decision variables. So what are the decision variables? They are already on the screen. Yes. What numbers are you deciding as part of the optimization? Yes. It's basically the binary variables, A, F, and L. Okay. You are deciding which ones are 0 and which ones are 1. And what about constraints? Can you guess one of the constraints for, say, F? What constraint defines the values that F can take? Remember, K is the index of the vehicle. Okay. So this vehicle K can go to how many customers as their first customer? Just one, right? So among all the F, I, comma, K's, only one of them can be equal to 1. Everything else must be 0. Right? So, yeah. Yes. So for each customer, only one truck can arrive. For each vehicle, only one customer can be the first customer, only one customer can be the last customer. Even when the vehicle is already at the customer I, it can only go to one other customer J, right? So for A, I, J, K also, there will be a summation which has to be equal to 1. So it has to go to exactly one customer, right? So just like you solved an optimization problem to compute the parameters for linear regression, you can write the optimization problem for solving Amazon split routing and you can solve it. Okay. In theory, you can solve this using traditional optimization methods like mixed integer linear program. Okay. Simple linear programs, etc. But it's not so easy because you will have a very large number of vehicles, a very large number of customers. Okay, so by the time your program actually computes the optimal answer, the day will be gone and you have no longer got any time for these trucks to actually deliver your parcels. Okay, and so whenever you have an optimization problem, which is either too complex to write down or is feasible to write down but too complex to solve in the amount of time you have available, you have to look at an AI type of algorithm. And you will actually come to see in a few slides time how we can go about solving this particular problem. There are the three types of machine learning at a conceptual level. As have you already covered this in the course? Supervised, unsupervised, and reinforcement learning. Yes. So quick refresher. What is supervised learning about? Sorry. Yes. So you have labeled data. The goal of your machine learning algorithm is to match the label as closely as possible. What about unsupervised learning? Yes. So it is pattern recognition. You don't have labels. You're trying to identify relationships in the data. And what is reinforcement learning? Correct. So that is how it works. But the reason you have reinforcement learning at all is because sometimes you don't know what the labels are. Okay. It's not an unsupervised learning problem in the sense you're not trying to find patterns in the data. You given a problem, such as an optimization problem, you don't know what the optimal answers are because we don't have the time to solve for an optimal answer. So you want an AI algorithm to solve this. It can give you some solution, right? Some sort of machine learning magical thing can give you a solution. You don't know if it is the optimal solution or not. Okay. So how do you provide the feedback for this machine learning algorithm to train? And the way you do that is by just evaluating what the objective function for this particular solution is. Okay. You don't tell the algorithm whether it's optimal or not, but you say that the objective function, which we defined on the previous slide here, is for a given set of decisions, A, F, and L, is this much. And then you let the program try again. Okay, if it comes up with a lower objective function now, which for us is good because we're solving a very problem, then you try to emphasize that you should do this more. If you come up with a worse solution, you should de-emphasize that particular thing. Okay, so that's how reinforcement learning works. It's based on feedback on what the program actually did rather than telling it what it should have done. Okay, so the way you would set up the Amazon problem, the fleet routing problem, is first of all, you have to train your algorithm, right? Before you actually deploy it in the real world. So you have to first go and procure the data. Okay. And the way you would procure data for Amazon would be you look at historical orders, you look at what the fleet characteristics are. So what is the capacity of each truck, what is the fuel consumption per kilometer, etc. Travel times between the places where you have set those orders. You can't just use that data directly because you want to generate more data for it to train on, right? So you can't just train on 1 month's history. You want to generate new problems based on how typically orders are given on a given day. Okay? So you take your historical data, you convert it into distributions or lookup tables of distances and times, etc. And so now you are in a position to create problems for it to solve. Okay? In the third step, you go to a simulation effort. So you have to train this algorithm in simulation. You can't do it in the real world. Okay. So you create a computer program that simulates how trucks move and it simulates where orders are generated and what the delivery times are, etc. So that's the build simulation step. Then you have to define some sort of simple policy, first of all, for you to figure out whether you're doing better or worse than what you already know. Okay, this is where you are able to provide feedback for reinforcement learning. And then you have to train an RL agent, which, as one of your colleagues said, depends on having an agent, having a simulation of the problem. So whenever you create a new problem, the agent has to give you what actions to take. In this case, these are the variables F, L, and A. So the agent decides what the values of those variables are. You figure out how well it did, and that goes as feedback to the agent. Okay. So this roughly is how it works. Obviously, we are not learning reinforcement learning today, so we are not going to details of how each of these steps work. But this is the rough idea of how you would go about solving an AI problem for managing Amazon's fleet. Okay. We'll go to more depths in a couple of slides again on how that can be done. But before we go to that particular, which was a multi-agent problem, you had multiple trucks to deliver. Let's look at what happens in simpler case when you have a single agent. Okay, this is a test setup that we had at the lab at TCS, in TCS Research, when I was there a few years ago. And this was an attempt to show how AI could help you pack parcels more efficiently for delivery. Right? So it's related to the Amazon problem in the sense that you have parcels which have to be shipped, but it's the step before you actually do fleet routing because you first of all have to pack those parcels into the trucks. Okay. So think of this as a simulation of packing parcels efficiently into trucks so that you can send more parcels on the same truck. What you're seeing here is a robot which has parcel manipulation capabilities. You have a parcel which it has picked up. There is a conveyor belt on which these parcels are arriving. Okay, that's this green thing that you see here. And you have three open bins on three sides of the conveyor belt in which the parcel can be put. Okay. The goal is as follows. A random stream of parcels coming on this conveyor belt. Okay. You don't have information about all the parcels that are coming in the future. Your camera system can pick up maybe the first three parcels on the conveyor belt. And your goal is to decide for these three parcels where to pick them up, how to manipulate them on the X, Y, or Z axis, how to rotate them, and which bin to put them in and where in that bin they should go. Okay. The final objective is very simple. You want to pack as many parcels as you can in a particular box. Alternatively, you want to minimize the amount of empty space in every bin. So this is an online optimization problem that you need to solve to figure out where to put each parcel and in what orientation to put them in. Okay. Now this needs to be solved using an AI algorithm. Assume that once you define where the parcel should go and how it should be put, you have a robotic controller which is able to do the manipulation properly and put it in the specified. But how would you go about solving this problem from a machine learning perspective, right? Assume you are given a camera system which gives you the size dimensions of each of these parcels. Think of it from a systems perspective. What would you need to do to solve this? Yeah. Any idea? So let's say you have got three parcels, right? Suppose you only look at the dimensions of the first parcel coming to you on the conveyor belt. And you are given a state of the bin, which is where all the previous parcels have been put. How would you decide when to put the current parcel? Yes. So one idea would be to fill up the floor of the bin first before moving to the top. Okay. What else? How do you figure out if it will even fit on the floor? Is there a feasible location for you to put this parcel on the floor of the bin? How do you know that? Yes. So you have to know what is the grid. So if you're looking at the bin top down, you have to know the height of each point in the bin, right? So think of the bin as a rectangle of this sort, okay, divided into a grid of certain dimension, say 1 centimeter cross 1 centimeter. If you know up to what height each cell in the grid is filled up, and you know the dimensions of the parcel that is coming up, you will know whether there is space for this parcel at all. Okay. And you can't just do it for the orientation the parcel is currently coming in. You have to look at it. What if you stand it on the top? What if you rotate it 90 degrees, etc. Right? So all the three dimensions of the parcel that you are currently coming up with are important. Now, you've done some amount of machine learning already. When you have a grid like this, right? Think of each cell in the grid as a pixel. What kind of neural network do you think would be able to help you with that sort of input? A convolutional neural. You may not have done CNN yet, but you do know that there is such a thing as CNN, which helps you manage images, right? So what I'm saying is the top-down view of the bin, which is converted into a 1 centimeter cross 1 centimeter grid, can be thought of as a pixelated image. And so you can leverage your knowledge of convolutional neural networks or image processing to tell you whether this parcel will fit into this bin or not. Okay. Intuitively speaking, what you do is give a photograph of the bin essentially as one of the inputs to your neural network. You would give a photograph of the parcel as another input to the neural network. And you would have a reinforcement learning sort of setup where the agent's action is to decide where to put the parcel. And the final feedback you give it is when this bin no longer can accept any more parcels, how much empty space remains in that bin. Okay. And that is effectively how we've been able to solve the problem. If you want more details, there is a paper cited, and I will share the screen. Or I think anyway, this meeting is being recorded, so you will have access to the reference. But the idea is that you have LDC here is what we call the bin. Okay, it's a long distance container. So you have the image of the bin coming as one of the inputs. You have the proposed location where you want to put the parcel as another input. And because you want to focus on the place where you're actually putting the parcel, you look at the border surrounding the parcel, immediately surrounding the parcel as a third, like a sub part of the image. Okay. So with these three inputs and with all of this, neural network machinery, which you've probably not gone into in detail right now, but you've seen some pictures at least I hope, you can do an evaluation of the proposed location. Okay. This type one output that you're getting at the end is your evaluation of how good this particular position is based on all the previous attempts you have done at bin packing as part of this reinforcement learning setup. Okay, and if you don't like this particular location, you can propose another location and try that as well. Okay. So you can use some sort of logic like your friend was suggesting, put the parcel on the floor first. But if there are many parts of the floor where you can put the parcel, you can try them all out using your neural network. Okay. And remember at the start when I was saying that you never have an AI algorithm operating in isolation. This is one of those examples. Okay, where good locations, proposed locations are coming from a heuristic or a rule-based algorithm, and you are only picking from among the quote unquote good location using your AI algorithm. Okay. The reason you can't just go for an AI algorithm is because the number of possible locations is huge. And you can't just ask it to say, specify my XY location where I should put the parcel. It has no idea of how geometry works or how gravity works. Okay, so we tried it. We could sometimes put parcels where they would topple into the other side of the bin, right? So it didn't make any sense to continue with that approach when we knew that there are some good heuristics to start. Okay, and so this is the kind of performance difference we could get from running this AI algorithm. The first few box chart tell you what is the min max. So this is your 50 percentile range. And these boxes tell you what is the 95 percentile range of percentage fit for each bench. Okay. And some of the heuristics that you have, such as building floor build, helps you let you start from the bottom and then you fill it up. Column build helps you, so basically are creating walls, right? So you put all the parcels on one end of the bin, then you do a second wall and a third wall, etc. That gives you roughly the same efficiency as floor building. You also have other heuristics, and then you have the AI-based algorithms. So you see that the gains are not spectacular. But when you're shipping stuff at Amazon's volume or Walmart's volume or over here Flipkart's volume, this change, right, from an average of 81% to an average of 83% could mean hundreds of millions of dollars over the course of a year, right? And that's why all of this matters. You might say that there's hardly any difference when you go for an AI algorithm. The point is that training and using an AI algorithm compared to the physical cost of your operation is negligible. The cost of training an AI algorithm. And with no additional infrastructure apart from a couple of computer chips, if you're getting $100 million savings, that's a big win. Okay. So in the real world, the takeaway is that you rarely see like going with stuff going from 40% efficiency to 90% efficiency because of it. Okay. But 2% efficiency is worthwhile changing if the operation is big enough. Now we come to the multi-agent aspect again to Amazon's fleet routing problem. You filled up all the trucks and the bins, etc. And you want to figure out how these trucks should move. Okay. One way to think about it is I am the dictator of Amazon. I am Jeff Bezos. I will decide where every truck goes. Right? Do you think it is feasible even for an AI version of Jeff Bezos to decide where each truck, Amazon's truck goes all over the world? No, right? So you have to divide the responsibility into multiple agents. Okay. And whenever you have multiple agents, they will each have their own objectives. Right. So Amazon's Mumbai warehouse manager will have certain objectives of how much his or her fleet costs to operate on a given day. So they will say, for local agents in between Mumbai and the Nashik, they will have a fight between the Nashik operator and the Mumbai operator to figure out who serves particular areas between Mumbai. Right? So solving any multi-agent problem, which you have to do to handle problems of scale, requires negotiation. Okay. So your AI cannot operate in isolation. You can't just solve your optimization problem. You have to solve a multi-agent optimization problem which brings in aspects of this field of maths called game theory. Okay, you may not have heard of it, but the idea is very simple. When you have two or more players of a particular game, and remember this game need not be literally a game, it could be any situation. Each of them has their own objective. Each of them has access to certain amounts of information. And you have to figure out what is the best way for them to negotiate and come up with a solution that is acceptable to everyone. Okay. So in this case, your step one is to decide which locations are served by which warehouse. Is it served by the Mumbai warehouse or served by the Nasik warehouse? In the second case, you have to decide how to do the routing because even from one warehouse, there will be multiple trucks that are traveling. And so you need a multi-step AI. And this figure is intended to be intentionally intimidating. Okay. So the reason for that is to show you that when you start with a problem as simple to define as we solve it, right? So you just need to figure out which truck delivers which parcel. At the end, when you build the AI algorithm, it will be a huge thing consisting of many components. Okay. So both of them simplistically right now, look at it this way. Remember the graph we have created of where each person's delivery location is? That's the graph that first starts for this model. This is a GE model, which is a graph neural network algorithm. This is specifically called a graph autoencoder. It incorporates what are the relationships between the locations where you want to deliver a particular parcel. Okay, there might be two locations which are relatively far away, but which are easy to access from each other because they are connected by a highway. And there may be locations in Kanjurmarg East and Kanjurmarg West, which are 1 kilometer away from each other, but need half an hour to travel. Right? So this graph has to incorporate all of this information, distances, as well as travel times. So the graph autoencoder does. It creates embeddings of each of these locations. There are features. There is a first stage agent which looks at what parcels are delivered or rather what customers are to be served by which warehouse. That's the first step decision. That's C2S. So this is cost to serve, which tells you which warehouse serves which location. There is a second version of this graph algorithm, which then decides based on the subgraph that a particular warehouse is now agreed to deliver the parcels to, how does it manage its own fleet? Okay, so the VRP stands for vehicle routing problem. So together, the C2S and VRP have to do a few iterations of negotiation to figure out, okay, you told me to deliver to these customers, but I'm just have one customer which is going to cost me an additional 1,000 rupees to go to because of my petrol cost or because I need one additional truck. So can this customer be delivered by some other warehouse? Okay, so it's not like a one-step flow that says, okay, you deliver to this people, and then the customer, the vehicles just decide to go. If the VRP comes up with a bad solution, you can go back to the C2S agent and try to renegotiate. Okay. Again, there is a paper reference for this, which you can find later. But in the last 5 minutes that we have, I want to go into a few things which we have not covered. Okay. The first one, and these are especially applied to robotic operations. Robots are physical things. So when you decide to do something with a robot, it doesn't happen instantaneously. Right? You've seen this in a car also. If you've driven a car, you will remember that when you press the accelerator, it doesn't just go from 0 to 90 kilometers per hour. It takes time. Okay, so the first challenge you have to consider, and which most AI applications right now don't consider, including reinforcement learning kind of applications, is the problem of physical delays in a system, especially problem if you are looking for research ideas. The second problem is that when you have robotic system which necessarily consists of what we talked about, which is sense, analyze, respond. Right? What does that mean? Sense part is whatever your sensors are measuring, it has to figure out what exactly it is looking at from the camera. Analyze in the sense of based on what you have measured, you have to decide what to do with that information, where to put the parcel, which customer gets served by which vehicle, etc. And then respond is actually take action on this. So take a decision on what should be done. When you have the sense analyze response cycle, you have to remember that there will always be errors. Again, when you look at Kaggle competitions, if you have participated in them or other AI algorithms, you will typically ignore any modeling errors, right? You might have an assumption that gravity is 9.81, but you don't, really account for the fact that at high altitude gravity is lower, for example. Right? So how do you handle errors in the models? Another thing. Adversaries, again, very interesting in the sense that for Amazon, we decided that all the things are cooperative, right? So at the end of the day, the warehouse managers want to deliver parcels efficiently. Fleet managers want to operate the trucks efficiently. But what happens when you have competitors, right? So what happens when you have an Amazon and a Flipkart operating in the same environment, for example? And the final thing is ethics. Okay, there are many places where you apply AI. For example, in generative AI, you will have heard about guardrails for LLMs. So there are topics that it should not discuss or information that it should not divulge, etc. That applies to all your physical or robotic AI applications as well. Have you heard of this philosophical thing called the trolley problem? If you're not, Google it. Okay, in simple terms, what this means is if you have a situation where something bad is going to happen, whether or not you intervene, the question is, should you intervene and reduce the damage or not intervene and let whatever was going to happen anyway happen, right? This is a very simple one-line way of doing it, but if you're interested, Google what a trolley problem is and look at it. But this brings into account the fact that, robotic systems, just like any other AI algorithms, also have ethical problems. Okay, so quickly speaking, in RL, if you remember, we said we will measure the state of the problem and we will take action. In this case, you have to account for the fact that you might be measure the state which is 2 timescale forward, right? And so your RL algorithm has to take an action which is going to be applied to the problem actually 3 timescales down the line. So there is a total round trip delay of 5 seconds or some sort of 5 timestamps. And so how do you train an RL algorithm when it has delays like this? Okay, and there are many interesting control theory concepts that apply to this sort of problem. There is error about robots moving in an environment. How do they figure out where they are exactly and what happens if they have errors in where they think they are? Okay, so in this concept called the general value function, again, not something that we have invented, but we have applied it. The idea is that you don't have a single hypothesis about where you are. Your robot thinks that it could be in one of 2 or 3 different places and it plans accordingly. And when it actually rolls this planning forward for a few time steps, it's able to actually understand where it really is in the environment. Adversary, this is a numeric competition. I don't know if it's still running or not, called Common Man. So you have two AI-based agents as a team playing against two other AI-based agents as a team. Right? And we have played this game called Common Man. This is very similar. So the idea is for these agents to place bombs to break down these walls and to go and find their opponents and place bombs around them in a sort of a trap so that the opponents cannot escape. Okay. The complexity is that neither of these teammates can necessarily see each other because they can only see a certain number of cells around themselves. Okay. And they cannot communicate with each other either. So this is more like, playing football where you look at your teammate and figure out what they're going to do rather than actually talk to them and decide what you want to do. Okay. And so how do you train AI algorithms that cooperate without actually being able to communicate with each other is another interesting aspect. And finally, on ethics, so when you have an AI algorithm which is guaranteed to respond to certain types of inputs, you also have to know when those inputs are not something that you want to handle. Okay, take a simple example. It is if you want to recognize cats and dogs, you have to recognize also when an animal comes in which is neither of these. Okay, and you should not force fit it to either be a cat or a dog. You have to call something that is out of distribution, right? So there are all of these aspects that you can think about. So to reiterate, AI is a lot more interesting and broad than just the narrow field of generative AI, which of course is interesting in itself, but not all research has to go into it. Surprisingly, we want to avoid AI as far as possible because remember, it will always give you lower performance than a traditional optimization algorithm. The only reason you use AI is when you have no other option, when your traditional optimization either cannot even or it can be formulated but not solved. Right?